Oh,
Okay, great, thanks. First of all, thanks for including my paper in the conference, and thanks for sticking around for the last presentation. So the title of this paper is Joint Bayesian Inference for DSGE Models. So the reason for the focus on Bayesian methods is because that's now the dominant estimation method within the DSGE setting. The focus of this paper is really to do with beyond the estimation of the parameters, so how we should think about constructing the central tendency for objects of interest beyond that, so functions of those parameters, such as the impulse response functions, the forecast error variance decomposition, etc. So traditional approaches within the literature really fall into one of two camps here. So either they follow the Bayesian VAR literature in simulating the posterior distribution for the impulse responses, and then at each point in time for each variable, you take the mean or the median as the central tendency. And then for the corresponding credible set, again, you treat each point independently as you go through. The issue with this is by treating each point independently, in general, you end up with a central tendency which is not consistent with the model that you take to the data. So it's not clear in terms of how you interpret that central tendency from the perspective of the model, which is important in a DSGE setting. The other thing is, by ignoring the dependent structure, we actually end up understating the degree of estimation uncertainty which is present in the credible sets. So that's the one approach. The other approach, which is more popular for either the forecast error variance decompositions, or particularly now at the moment within the estimated Hank literature, is to first estimate the parameters and then fix those parameters at their posterior mode values and use those values fixed to then generate the objects that we're interested in, so the impulse responses, forecast error variance decompositions. There's two issues here. So the first is, by collapsing the posterior distributions into a point estimate, you're completely ignoring the estimation uncertainty that sits behind that. The second is to do with whether the mode is able to give a good measure of the central tendency for the distribution of the impulse responses. So the mode is not invariant to nonlinear transformations. So a nonlinear transformation of the parameters to give you the impulse responses or the forecast error variance decomposition means that by fixing the parameter values at their modes, we don't actually get a good measure of the center of the joint distribution for the objects that we're actually interested in. Okay. So the question is, there's two problems that we're trying to solve here. The first is how we can construct a good measure of the central distribution, which allows us to both be at the center of the joint distribution, but also give us something that we can interpret entirely through the model equations. And the second is how we can properly characterize the estimation uncertainty which is present. And it turns out that Bayesian decision theory allows us to solve both of those issues. Okay, so the contributions of this paper, there's three. I'll have time to cover two of them today. So the first is, obviously, I'm bringing the joint inference procedures to DSGE models. So previous research has really focused on VARs, but it turns out that joint inference and the issues which are present are actually more prevalent in a DSGE setting. The reason for this is because you have much fewer parameters than you do endogenous variables compared to a VAR. Okay. The second is that I take more of a stance on the type of loss function that should be used. So Inouye and Killian, which is the paper which is closest related to this, also use Bayesian decision theory, but they remain quite agnostic about the choice of loss function that you should use in practice. If by remaining agnostic, you are able to solve the model inconsistency issue, but you're not necessarily able to gain a central tendency, an estimate for your central tendency, which is at the center of the joint distribution. So I suggest a loss function which is more grounded in the multivariate statistics literature, which enables you to do that. And finally, which I'm not going to have time to cover today, I discuss some considerations which are important in a time series setting, which have been overlooked by previous papers imposing this kind of framework. Okay, so let me start with the traditional approaches and try and explain or point out to you where those issues are. So first of all, let's start with the point-wise approaches. So what we do is we estimate the parameter values, and then for each draw from the parameter vector, the posterior distribution for the parameters, we then simulate the posterior distribution for the impulse responses. Then at each point in time, for each variable in each shock, we then take the mean or the median of those at the distribution at that point in time. So what we're doing when we do that is we're implicitly assuming that the impulse responses are independent, both across time and variables. And this is obviously quite a strong assumption to be making in a in a macro setting because we assume that macro variables exhibit persistence. So across time there'll be dependence across time. And also in a general equilibrium setup, we expect there to be dependence across variables. So the response of one variable to a shock will then likely have knock-on effects on the other variables in the system. Okay. So this is problematic in terms of the way that we set the model up, but it's also an issue in terms of how we go about getting our central tendency. The issue is by taking the mean or median at each point in time, we don't guarantee that we're using the same structural parameters to gain for each point in time. So what that means is the impulse response for inflation to a monetary policy shock at horizon 4 might be generated by different structural parameters to the mean or median impulse response to inflation following a monetary policy shock at horizon 5. So the issue then becomes how much of that movement between horizon 4 and horizon 5 can be attributed to the model equations, which is what we want to be able to do to interpret the model, and how much of it is due just to the change in the parameter values. So drawing economic conclusions based on that central tendency then becomes problematic because it's not certain how much of it's driven by the model equations. Okay. So let me give a very simple model, not in a DSGE setting, to hopefully make that point a bit clearer. So go to a simple univariate AR1 process. So equation 1. I'm going to assume that phi is normally distributed with mean phi m and sigma phi as its variance. Okay. So for each draw from our posterior distribution for phi, we then simulate the full path of the impulse responses, which is given by the first row of this table here. So these are consistent with the model. So for each draw of phi, we get model-consistent impulse response functions. The issue comes when we try and characterize the central tendency of this. So the standard approach is to use the posterior mean or median. I'm looking at the mean here just because it's easier to characterize for the slides, but the same arguments also hold for, or similar arguments hold for the median. Okay. So at horizon 0, there's no issue because the distribution is degenerate because phi to the power of 0 would always be 1. At horizon 1, we just get back the mean of our phi's. So for all of the phi's that we draw, then we take the expected value of that, which gives us the mean of our posterior distribution, phi m. At horizon 2, for the central tendency that we're generating to be consistent with the AR1 that we take to the data, we would expect this to just be phi m squared for it to follow the AR1 structure. But we actually have this additional term, which comes from the variance formula here. So the issue is that there's no value of phi that we can select for the posterior mean, which would actually satisfy the AR1 structure in this setting. So this is the problem that we're trying to overcome, because we want to be able to produce a central tendency which can be explained by the model that we take to the data. Okay. So it turns out that this is always an issue, provided that the number of estimated parameters in your model is less than the number of impulse responses that you're interested in. So here, the number of impulse responses is the individual points, so the number of endogenous variables multiplied by the number of shocks, multiplied by the horizon of interest. And this is, in the paper I formally show this, but just kind of the intuition behind this is that this is always a problem in a DSGE setting. And the reason for that is because in general in DSGs, you have a lot of endogenous variables and not so many parameters. So in a VAR, because of the square structure, you can sometimes get away with this in the limit. But in a DSGE setting, this is almost always creates this discrepancy between pointwise and the joint approaches. Okay. And then finally, just very quickly on pointwise approaches, just to say that the highest posterior density intervals are also generally done pointwise. So again, we're ignoring this dependent structure over time. And it's well known that this leads us to mischaracterize the degree of estimation uncertainty that we have. Okay. The other approach, which I've already covered, but just again, so is to collapse the posterior distribution into point estimates. So typically people use the parameter modes, but some papers use the parameter mean as well, the mean of the parameter distribution. This solves the issue, which is in the pointwise one. So we're always using the same structural parameterization. So you can interpret your impulse responses through the lens of the model that you take to the data. However, the issue here is that you don't guarantee that you get a good measure of the central distribution, and also that we're completely ignoring estimation uncertainty. And I'll show you an example later where this plays quite a big role. Okay. So the way to overcome this, or at least the way that I propose to overcome this, is to use Bayesian decision theory. So the key difference here is that we're minimizing some loss function, but we're minimizing the entire vector of impulse based on the entire vector of impulse responses simultaneously. So we're no longer looking at each individual point in time, but we're assessing this loss over the entire vector. Okay. And this capital theta here contains the set of all impulse responses which are possible to be obtained given the structure of our model. So we're no longer looking over the entirety of the real numbers, we're looking over a specific set which is feasible given the model that we take to the data. So that's really the key difference between the pointwise approaches and this joint approach. And it turns out that if you drop the assumption that you have to pick over the feasible set, and if you pick over individual elements, the Bayes estimator here, which is in equation 4, will actually give you back the vector of medians. So the standard pointwise approach. Obviously, in practice, we have to numerically approximate this. So we take m draws from the posterior distribution, and we take the sample average of these. And as the number of draws goes to infinity, equation 5 will obviously converge to equation 4 by law of large numbers. So one of the contributions of this paper is to be a bit more specific about the loss function that's used. So the idea behind which loss function we should use should be motivated by the multivariate statistics literature. So we want our central tendency, or the vector that minimizes the loss, to be close to the center of this joint distribution of the impulse response vector. So the loss functions which have been proposed in the literature mostly don't achieve this for various reasons. So additively separable loss functions generally are quite close to their pointwise counterparts. And the angular loss, which is also proposed by Noah and Killian, will give you the most likely shape of the impulse responses, but not something which is closest to the central distribution. Okay. One loss function which does do this is the direct delta loss, but computationally this is very expensive, so people don't tend to use it in practice. So instead, what I propose is I use the Euclidean norm as the loss function, and this has quite a nice interpretation in terms of multivariate statistics in that without the constraint, so without forcing it to be within this set theta, this Euclidean norm would give you the spatial median, which is a well-regarded measure of the central tendency for joint distributions. Okay. So you can think of the loss function or the Bayes estimator established under this loss as a constrained version of the spatial median to lie within the feasible set of impulse responses. Okay. So, and then for the joint credible sets, we should also be taking into account dependence across time and across the full vector of impulse responses. So in practice, what we do is we look for the expected posterior loss to be less than a certain threshold. In practice, what this works out as being is we take the 1 minus alpha times 100% of impulse responses that generate the lowest losses. So this is a visual representation of the joint credible set rather than the credible set itself. And as the number of posterior draws approaches infinity, we converge to the true joint credible set. Let me quickly go over the empirical application. So I use the empirical application from Boll, Goy, and Strobel, which is a large nonlinear DSGE model. So it's basically the base of this model is Smets and Wouters, but it also adds financial frictions and quantitative easing from Gertler and Crowley, 2013 paper, and also has a zero lower bound. So it adds quite a lot of nonlinearity to the model. And we treat the zero lower bound as an occasionally binding constraint. Yeah. Yeah. So the first one is to do with, this is the pointwise comparison. So the blue lines here are the pointwise approaches, so the standard approaches in the literature. So the solid blue line is the posterior median impulse response. So this is the one which is the most popular in the literature. It's what Smets and Wouters do, and it's what, because of that, it's what most people use as the central tendency for impulse responses. And you can, the red line is the Bayes estimator, so this is under the Euclidean norm loss. Dashed blue lines are the 90% highest posterior density interval calculated on a pointwise basis. And these gray lines are our visual representation of our 90% joint credible set. So although there's some differences, so the Bayes estimator produces less persistence in output following a productivity shock, in general, the central tendencies are not too dissimilar in this case. The big difference really is to do with how we characterize estimation uncertainty. So you can see that the gray lines here are very far away from the dashed blue lines. So it seems like the main benefit of using these joint approaches, at least in this setting, is to do with the fact that we're understating the degree of estimation uncertainty in conventional approaches. Okay. So now let me turn to the forecast error variance decomposition, so second part of this example. So in practice, what most people do here is they use the mode of the parameter distribution. The reasoning for this is because by using the same parameterization, you guarantee that the forecast error variance decomposition is sum to 1. So that's the most common way that people use it in practice. And normally what you see in papers is something that looks like this plot here. So based on the parameter, the posterior mode of the parameters, you generate this kind of distribution, or these point estimates. So even at a point estimate level, the Bayes estimator gives quite different responses here. So you see that the marginal efficiency of investment shock plays a much smaller role relative to under the parameter posterior mode, whereas a productivity shock would play a much larger role, as would a risk premium shock. The thing that I wanted to point out here, though, is not the point estimates themselves, but rather the estimation uncertainty that sits behind these. And that's not something that's possible using the posterior mode for the parameters because we're collapsing this posterior distribution into a point estimate. But it is something that you can do with the Bayes estimator. So if we look at the 4 largest shocks in systems, so we'll look at productivity, risk premium shock, marginal efficiency of investment, and then also the price markup shock, so the 4 largest shocks in our system. And we look at the estimation uncertainty that sits behind those point estimates. You can see that there's absolutely there's an enormous amount of estimation uncertainty that's present there. Okay, so although the marginal efficiency of investment shock is shown to be the largest when we look at the point estimates, if you look at the 90% joint credible set here, the amount of variation in output that can be explained by this shock is somewhere between 5% and 85%. So it's absolutely an enormous amount of estimation uncertainty that we're ignoring when we use the posterior modes to do this. And you can see as well that this degree of estimation uncertainty is actually present across all of the forecast error variance decomposition. So we see that. So I think that's an important thing to acknowledge when you're estimating these kind of models, is that although the point estimate would suggest these things, there is actually a large degree of estimation uncertainty that sits behind them. And the Bayes estimator allows you to characterize that. Okay, so let me wrap up. So what I've shown in this paper is that using Bayesian decision theory allows us to construct objects of interest, such as the impulse response functions, the forecast error variance decomposition. But you can also extend this to historical decompositions or forecasting, if you're interested in doing those things. And they allow us to preserve the economic structure of the model that we're taking to the data. And the choice of loss function as the Euclidean norm allows us to preserve or generate a good measure of the central tendency for the joint distribution for the impulse responses. The advantage over the current approaches is that it's both computationally feasible and grounded in the multivariate statistics literature. Okay. And then finally, the thing which I didn't have time to cover today, which is that researchers should also be careful about the horizon length that they select when you're using joint approaches. The reason for this is because the vector of impulse responses is obviously a function of the horizon length. So if you choose an arbitrary long horizon, it skews the results. So it's something that you should bear in mind, and it's something that's not been acknowledged really in the existing literature on this. I have a very simple approach for correcting that in the paper, but there's probably more to be done on that. And with that, I'll finish. So thank you.